In this next example, we're going to see that there are a lot of interesting fields out there. In particular, we're going to look at an example you're going to see over and over again if you go further and take get into our master's program and then take 6016, which is the graduate algebra course. And in that graduate algebra course, you care a lot about fields like this. So I claim this is a field. What is it? Well, elements here look like a rational number plus a rational number times root 2. And we have to say what the addition operation is. The addition operation is what we'd expect it to be. You combine like terms. So a plus c plus b plus d root 2. And the multiplication operation is what you would expect it to be. You multiply, and you get I should put a dot here to indicate its multiplication. And when we multiply, we FOIL. So our first terms are going to be AC. Our outside terms will be AD root 2. Our inside terms are going to be BC root 2. And then we're going to get a BD root 2 squared. But root 2 squared is just a 2, right? So that's a 2. A lot of 2's there. So really, the portion that doesn't have a root 2 on it is AC plus BD. And the portion with a root 2 is AD plus BC root 2. Okay, so it's a field with these as our binary operations. We can see that when we add, we again get, if A, B, C, and D are the rational numbers, then A plus C is a rational number, and B plus D is a rational number. So we get a rational number plus a rational number times root 2. So we get something in our set. So it is a binary operation. It is closed under addition. And also, AC, if A, B, C, and D are rational numbers, then this whole expression is a rational expression. And similarly, AD plus BC is a rational expression. So this element, although it looks kind of complicated, is also an element of Q adjoin root 2. Why? Because it's in the right form. It's a number plus, it's a rational number plus a rational number times root 2. So both of these operations, plus and times, are closed. Well, let me put it like this. Q adjoin root 2 is closed under plus and times. Okay, so let's go through and check that it is a field with these operations that's closed under. Now, some of these checks I'm not going to do. So let's check the additive properties. It's associative. Well, yeah, it's associative. All we're doing is we're combining like terms. The addition is combine like terms, which is an associative property. In particular, it's combine like terms and then add with the plus in Q once you combine the like terms. And that's an associative operation. We proved it. So I'm not going to go through the proof. I will do some of them to show you how they go, but you can prove associativity. I'll do commutativity because that's not so much writing. We need to show that A plus B root 2 plus C plus D root 2 is equal to C plus D root 2 plus A plus B root 2. That is, we need to take two random elements. What do random elements look like? They look like a rational number plus a rational number times root 2. So here's our first random element, and then our second random element is C plus D root 2. We need to take them, we need to add them together, we need to add them in the reverse operation and check that they're the same. So let's do that. This is a question mark. Remember, our addition operation is combine like terms. So on the left-hand side, we get A plus C plus B plus D root 2. And on the right-hand side, we get C plus A plus D plus B root 2. So are these equal? Well, let's leave the left-hand side alone for a second. The right-hand side, we're adding as rational numbers in these parentheses. An addition of rational numbers, we know, is commutative because we proved it. Now we're not writing these as fractions. We could. So let's conclude this, and then I'll continue that thought. We have the same thing on the right and the left, so is it commutative? Yeah. So let me just take a slight pause here. Give me an orange pause. We could, if we wanted to, write these as honest rational numbers. It's a lot easier to say A, B, C, and D are in Q than to say A over B, C over D, E over F, G over H are in Q. And then to write out a general term here like this, that's a lot more writing than just to say given A, B, C, D in Q. With the understanding that if we wanted to care about the fact that it was a fraction, we could then go and write it as a fraction. So, you could do this. You could assign a variable to the numerator and denominator, but I'm going to encourage you not to because it's irrelevant for the argument. All right, it's commutative. Let's see, what else? There should be a 0. There should be an additive identity. So 0 sub q root 2 is our notation for that. That's just 0 plus 0 root 2, which I'm going to write as just 0. I'm going to mean all this. These are all mean the same thing for this. So what happens if we add 0 to a random element of q adjoin root 2? Well, we're supposed to add the real and imaginary parts. So that's a plus 0 plus b plus 0. And that's a plus b root 2, because 0 is the additive identity for q. Great. Do we get itself when we add 0 on the left? Yeah. And I'll leave it to you to check a plus b root 2 plus 0 is a plus b root 2. So we check this one. You got to check that one. Great. There's an identity. Cool. What about inverses? All right. So given a plus b root 2 and q adjoin root 2, the additive inverse is what you would expect it to be. It's negative a plus negative b root 2. You check. It's not hard, I promise. And then we have to go to the multiplicative properties. Associativity. I'm also not going to do associativity. That's a nightmare. It's good for your soul to do once in your life. I've done it about 1 billion times, so my soul is extra hardy. But what you would have to do is you would have to do these products, do that one, and compare with first multiply the first two terms and then the third term. So that's a lot of foiling that you can do, and it's good for your soul, but you check. Some algebra practice. 6, commutativity. All right, I'll do commutativity because although it's a little complicated, it's not that hard. So let's multiply a plus b root 2 and c plus d root 2. So we worked out a formula that you can go back and look at. I'm just going to write it down. Or you could FOIL it out and you get the same thing. And then I'm going to do the other way as well. Let's see, CB plus DA. All right, there we go. Now, of course, multiplication in Q, remember, because A, B, C, and D are in Q. We don't have to preface that. I'm just reminding you that they're in Q. If we were to multiply elements of Q, well, I know that multiplication in Q is commutative. Why? Because we went and we proved it. We got down in the dirt and we proved it. We also know addition in Q is commutative. So I can rewrite both of these expressions, and aha, they're the same. Great. Nailed it. Number 7. Identity. Or no, yeah, identity. What do we think the identity is? Well, I'm sure that you can convince yourself that the 1 here is 1 plus 0 root 2. And then you check. Check that when you multiply that with something, you just get that something back. 8, multiplicative inverses. All right. We already, we saw that additive inverses are kind of easy. The multiplicative inverse is not so much. And so let me show you a way that you can go about this. So what we really want is, well, if A, B are not both 0, so that the element A plus B root 2 is not 0, then how can we try to figure out what 1 over A plus B root 2 is? First of all, we don't know anything about this right now because, well, it doesn't look like a rational number plus a rational number times root 2. It looks more complicated than that, right? It looks like 1 over that. This is not of the right form to be in our set, so we have to move it into the right form. So what can we do here? Well, I think we can multiply by a minus b root 2 over a minus b root 2. And when we do that, we're going to get a minus b root 2, and the denominator is going to be a difference of squares. We're going to get a squared minus 2b squared. Now this is going to be fine and good because we can rewrite this as a over a squared minus 2b squared, and then plus negative b over a squared minus 2b squared root 2 by moving into their own fractions. And if a and b are rational numbers, then this guy without the root 2 is going to be, again, a rational number. And the second guy, the one on the root 2, is also going to be a rational number. And so we're good. But there's a slight caveat here. We have to check that a squared minus 2b squared is not 0. Right? Because if a squared minus 2b squared were 0, then, well, that would be bad, right? Because we would be dividing by 0. So let's go and check this. We have to make sure this doesn't happen. So let's do it. Suppose, for now, that a squared minus 2b squared is 0. And this is equivalent to saying a squared is 2b squared. Since both a, b, well, what do I want to say here? We know that a and b are not both 0, and this equation here says that actually they're both non-zero. Since a, b are not both 0, a squared is 2b squared tells us they're both non-zero. Because if they were both if one of them was non-zero and the other one was 0, this equation couldn't hold. Okay. Then what we're going to do is we're going to divide by b squared, and that's equivalent to writing a over b squared. And then this is equivalent to q squared is 2, where q is a over b. That's again a rational number, right? Because a is a rational number, b is a rational number, and we can divide rational numbers. Great. But one of the first things you learn when you're learning how to prove by contradiction is that q squared is 2 has no rational solutions. A q is plus or minus root 2 is not a rational number. It's very much not a rational number. So if it was true that we got 0, a squared minus 2b squared was 0, then root 2 would be a rational number, but it's not. Thus, a squared minus 2b squared is not 0 when a and b are rational. And so our denominator, if we scroll all the way up, makes sense to write down. We can write down this denominator just fine. Okay, great. So we have a multiplicative inverse now. What's the multiplicative inverse of a plus b root 2? Well, it's a over a squared minus 2b squared plus negative b over a squared minus 2b squared times root 2. So this is a cool formula for an inverse here in violet, or lavender, whatever color this is. However, the formula is not anything you haven't seen before. It's kind of unenlightening even. It's just rationalized. Okay, that's all we did was we rationalized and we got this formula. Okay, so we have inverses, good. And then 9 and 10 are almost the same. We have the left and right distributive properties that I'm not going to check. I think your book calls distributive 1 and 2. But let me just show you how you might go about checking distributive 1. You have to take a random element in our set, multiply it with the sum of two random elements in our set, and then compare that with multiplying the first guy with the second one, and then adding that to the product of the first one with the second one, or with the third one. So how do you do that? Well, you have to multiply and add everything out, and then check that you get the same thing. And it's a similar thing with the second distributive property, or the right distributivity.